In the previous lecture, we saw that analog phase detectors can be used, but unfortunately, they are capable of detecting the phase error only over a very narrow range. That too, the phase difference should be 90°. So it measures the slight deviation about the 90°. With the XOR gate, we found that they can also be used to detect the phase error, but they are capable of detecting the phase error up to pi degree. In this lecture, we will see two phase detectors uh, which will be processing the digital signal. That means the reference and the divider output should be uh, square waveform. And we will see that they have a wider range of phase detection capability. The first phase detector that we will study is based on SR latch. So here we have SR latch, which has output Q, and this latch is governed by this table. So when we have 10 input, we get 10 output. When we have 01 input, we get 01. When we have 00, we get the previous output remains unchanged, and when we have 11, we actually get 00 output. But we will see that this fourth input is avoided. This will not allow us to use this SR latch to detect wider phase error between the input reference and the divider output. So we will try to avoid this input, 11 input, by actually feeding the very narrow pulse for these two signals at their respective rising edges. If we have VR like this, so what actually will be fed to this SR latch? A narrow pulse around this rising edge. So what actually will be feeding is say VRP and DRP. These kinds of pulses will be fed. And this is done just to avoid this 1-1 input condition. And if we use this condition, we will be able to detect phase error only from 0 to pi. And with this kind of pulse kind of input, we will see that phase can be detected up to 2 pi. So now we are going to take a few cases to find out this output and draw the characteristic of this SR latch based phase detector. So we are going to take uh, VD and VR. For example, this is our VR, and then we are going to take VD, which has some phase uh, error with respect to the VR signal. So this is VD, and as was pointed out, we will be actually extracting a pulse and then feeding this pulse to the SR latch here. So we will be actually feeding this and this to the SR latch. Now let us see that what will be the output if we have this scenario. So here also we have these rising edges for these pulses, but the pulses are so narrow that pulses themselves will be treated as rising edge. So we now going to find the output. So here we see that whenever S is 1 and R is 0, output is 1. And whenever S is 0, 1, we have 0, 1 and 0, 0 maintains. And this kind of pulse will be able to avoid this occurrence of the fourth input, which reduces the phase detection range. So now here we see that when VR pulse, this becomes 1 for short duration, output will be uh, changed to 1. And then it comes back to 0. So we now have 0, 0 condition. So here we see that we will have same value, and this same value will continue till the rising edge or the pulse for VD comes. So it comes here. So when we have a pulse for VD, we have 1 here and 0 for the reference signal. So this will be brought back to 0. And after this, we see that both the pulses, they have 0, 0. So this condition is going to remain till the next rising edge of VR, the reference signal occurs. So here we have 1 and 0, so it becomes 1, and then it becomes 0 after a very short duration, and the other pulse is 0, so it remains in the previous state, that means state of 1, till the rising edge of VD occurs. So it is again brought back. So we see that this SR latch is able to sense the gap between two consecutive rising edges. And actually, this is what is going to be the phase error between these two signals here. So we can see this thing in the circular motion form. So here we see that we are as rising edge here. So this is going to be the location of the reference signal, and VD becomes 1 after a certain positive duration. That means it must be having this kind of location. So this is the location of the divider output signal. So this much is the phase error between two signals, and both the signals are then rotating. So if the frequency is same, then this phase error will remain constant. Otherwise, it will keep on changing depending upon whose frequency is more. So by the way, here we have taken example when the frequencies are equal. So this is omega r, and this is equal to omega d. So at this stage, we are focusing on the phase error. So we see that now we have a pulse at the output Q, whose width is directly related with the phase error between these two signals. Now, as the gap between these two edges increases, the width of the pulse is also going to increase. And the DC part of this output Q, which is going to be the average of this, will be proportional to this phase error. So as the gap between the edges of two signals, VR and VD, increases, this width is also going to increase. So the DC content of this output is also going to increase. So this will be able to give the idea of the or the amount of the phase error between two signals. Now let us try to increase this phase error and see that what is the value up to which it will be able to give output. That means what is the error up to which this width will increase. We have now taken different signal which has rising edge quite away from the rising edge of the VR signal. So at this moment, the phase error or the mismatch between the rising edges of the two signal is going to be this much wide. So here we see that when the rising edge of VR occurs, That means when this pulse occurs, so we have value 1 and 0, 0 for VD. So we will have 1 here and for short duration, but after that we have 0 for reference and 0 for the difference. So it will maintain this value, which is 1, and then this will be maintained till we have the rising edge of the PD signal, so which occurs here. And at this stage, we have 1 here, but 0 for the reference signal. So it will be brought back to 0, and this will remain 0 till the rising edge of VR occurs, which is here. And this process will continue. So here we see that this value is 2 pi and this value is 0. So 2 pi or 1 cycle of VR is from here to here. So we see that as this phase error increases from 0 to say pi, then beyond pi also, then we see that the width of this output pulse, it keeps on increasing. And you can see that this pulse width will increase till 2 pi. That means the DC content of this output Q will keep on increasing as this phase error increases from 0 to 2 pi. So unlike XOR gate, which can detect or which produces the linearly increasing output only up to phase error of pi, this is producing the phase error or this is producing the output for the phase error up to 2 pi. So in this case, if we try to draw the average value, average output with respect to the phase error, then we see that this value will increase from 0 to 2 pi, and then this will repeat like this. So this is the average or the DC of Q. Now, what about if the phase error is negative? That means here reference signal lags the difference signal. Here we see that reference is ahead of the difference. So for that case, we have to see that what will be the scenario. So this is case 2 and previous was say case 1 when theta r is greater than theta d. So in the case 2, we have theta r minus theta d negative. So we have this scenario. Now say theta d, or that means omega d is here, phasor is here, but omega r phasor, the reference signal phasor is here, and this is the amount of phase error. So omega r minus omega d is negative, and both are rotating in this direction. So we now have a scenario, and then there will be VRP pulse. This, but VD is going to be of this form. We will have a narrow pulse for VDP at the rising edge of VD signal. Now we want to know what will be Q. So we start with the assumption that Q is initially 0. So we find that we had 0 for VR or 0 here and 1 for VD. So what we are going to get is 0. So it was 0, it will remain 0. And then after a short duration, then we have 1 for VR and 0 for VD. So at this moment, it will become 1. And then for short duration after this pulse width of VRP, we again have 0, 0. like this. And this continues till here, till the next rising edge of VDP. So this will continue up till here. Now we see that similar thing will then occur. So this will be 0 till this moment, because after this we have 1 here, 0 here. So it will give rise to 0, and then we have 0, 0, and then finally 1 and 0. So it becomes 1, and this phenomena repeats. So here we see that over a range of 0 to 2 pi. So this is 2 pi point and this is 0. So this is 2 pi and this is 0. So here we see that if there is a negative phase error like this, then we get a white pulse, which we used to get earlier for large phase error. So here we see that when this phase error, this much is the phase error. If this phase error increases, then this pulse width is going to decrease, because now the phase error is proportional to this much gap, and this gap corresponds to moment when Q is 0. So as this phase error increases, that means as we pull this edge towards the right side, increasing the gap between VR edge and VD edge, so this pulse width, this is going to become narrow and narrow. So a small negative phase error gives rise to large pulse width for Q. That means large DC value for Q. And as the negative phase error increases in the magnitude, this DC content of Q or the width of Q is going to decrease. So what we find is that for negative value, we are going to get a response like this. So initially it will be large, and then it will decrease like this. So this is going to be the characteristic of SSR latch based PD, phase detector. Now we are going to talk about second digital phase detector, which is much more versatile compared with this SR latch based, and it has a wider range also. And this one is called phase frequency detector. So here we see that we not only have phase detection capability in this circuit, but as the name suggests, it is capable of detecting the frequency difference also between the two input signals. So here for the SR case, we have considered only the phase difference between the two signals. So this, in terms of block, of course, has two input like the SR case, and we will be calling these inputs as VR coming from reference and VD coming from the divider. But it has two outputs, although SR latch also has two outputs, but we use only one of them, the Q output. But here we have two outputs as well. And both these outputs are used together to find out the voltage, which will be ultimately fed to the VCO for reducing the phase error between these two input signals. And this first output is called up output. The second is called down output also. So we will talk about that why we have these two designations for these two outputs. So this PFD is best described first in terms of the state diagram, and then state diagram can be used to find out these two outputs, and then find out the characteristic of this phase frequency detector. And then later on we will see that how do we implement this in terms of digital circuitry. So first we will see the state diagram of PFD. So this is a state machine with three states. So first state will be called state 0, and in this state this QR and QD both are 0. So this QR is equal to 0 and QD also equal to 0. Now what happens is that if there is a rising edge occurring at VR input, then it moves to state 1 where we have QR is equal to 1 but QD remains 0. So it moves to this state when VR gets a rising edge. And if in this state VR rising edge occurs, then system remains in the same state. That means QR will remain 1, QD becomes 0 or it remains 0. So as long as VR rising edge occurs, it will remain in this state 1. However, if in state 1 the rising edge of the difference output occurs, then the machine or system returns back to state 0, the previous state. Now, if in state 0, rising edge of Vd occurs, then what happens? The system moves in a state where QR output is 0, but QD output becomes 1. And it remains in this state as long as the rising edge of Vd occurs. However, if the rising edge of VR occurs, then system returns back to state 0. And this one is called state 2. So these are the three states for this machine. So using this state diagram, we can find out what will be the output QR and QD, and then we can see that how the phase error between VR and VD signal manifest in terms of these two outputs and how those outputs can be used to detect the phase error. So first we will take the case of equal frequency scenario, and then we will later on move to scenario when frequencies are different. In fact, frequencies are very different from each other. Wide frequency gap between VR and VD. So we are going to consider various cases. So first we will talk about case 1 where the frequency are equal, but then there is a slight phase mismatch between the two signals. So as usual, we will first consider the case when VR is here. This is omega R and this is omega D. So we have this much of positive phase error. So theta E is theta R minus theta D. So this corresponds to taking signals of this form. Here we will see that we need not create a pulse out of these two input signals. This signals in their natural form, in this clock form, are enough to get the meaningful output from this phase frequency detector. Here we have this much of phase error between the two signals. Now we will assume that QR and QD, they are both in 0, 0 state in the beginning. So both are 0, 0. See that both are in state 0, but then the rising edge of VD occurs before the rising edge of VR. So what happens is that system moves in state 1, where QR is going to be 1 and QD remains 0. Here. Then we see that after a delay corresponding to theta E, the phase error, rising edge of VR occurs. So system is in state 1, and then here a rising edge of VR occurs. So this will bring back the system to state 0. And QD, of course, remains 0. And after that, we see that we will have to wait till this moment, because this is where the rising edge occurs. So keep in mind that this state machine only senses the rising edge, and it does not react to labels, 1 or 0 labels of these two signals. And we need not do anything else to create pulse for these signals. The system itself is sensitive to the rising edges inherently. So this will remain like this till here, and this will also remain like this till here. And then once again, in state 0, rising edge of VD occurs, so this becomes 1, and then rising edge of, so this goes to state 1, and then it is brought back to state 0. And in this fashion, output continues. The actual output, which we will use to find out the DC or the average value, is going to be QR minus QD. So here we see that this is going to be high and then 0, then high and then 0. So here now we see that if we increase this gap between the two consecutive edges of these two signals, then the width of QR is going to increase. That means width of the different signal is going to increase. That means the DC content of this different signal is going to increase. So the DC content of this difference output signal will be proportional to this phase error that we see between the two signals. So we can uh, see that as this phase error increases from very small value to, in fact, up to 2 pi, so the width is also going to increase from 0 to 2 pi. So for the positive phase error, this value is going to increase from 0 to 2 pi, like that of the SR latch case. But unlike SR latch, we need not create pulse to make this circuit work. Even in real life, at this stage, we are only talking in terms of state diagram. So this is QR minus QD average, or the DC of this signal. So now let us see that what happens when we have a reverse scenario. That means when reference signal lags behind the different signal. So we now have case 2 where uh, theta r is less than theta d. That means theta e, which is theta r minus theta d, is going to be negative. So now we have this scenario. That means say theta d is here. So difference phasor is here, and the reference phasor is here, and this much of negative phase error exists. Now we have this type of waveform. So VR is like this, and VD is like this. Here. So these are the rising edges of two signals. So here you can see that this much is going to be the phase error and this is negative. So now let us see that what will be QR and QD. So we see that, of course, we assume that in the beginning both are in state 0. So we see that the rising edge of VD occurs first. So this QD will become 1 and it will remain 1 for short duration, because then after short duration rising edge of VR occurs. So here what happens is system goes into state 2, and then after a short duration corresponding to theta E, the system is brought back to state 0, because the rising edge of VR occurs. And then this will continue till the rising edge of, because that is what happens first. So we have this scenario, and then at the rising edge of VD again we have a pulse here for theta D, sorry QD, and then we have 0 for the rest of the duration, and QR remains 0. So this is what we are going to get. Now if we see the uh, QR minus QD, then what we are going to get, this is 0 value. So we are now going to get negative pulse. So this is 0 and this is minus 1, like this. So here we can see that we again have pulse of width which is proportional to the phase error, but then the sign of this magnitude or the value, the pulse width, also conveys the direction of the phase mismatch. So earlier also we had the similar width of the pulse, but it was in positive direction. So now if you see the DC content, this DC content is going to be negative. So now QR minus QD average is going to be negative. And as you can see, when this gap between them increases, which corresponds to the phase error, then we are going to get a wider and wider pulse width. So what will happen is the DC content of their difference is going to increase, but of course it will be more and more negative. So what we are now going to get is characteristic like this. So here we have theta E, but now this is negative. And here we saw that when this theta E increases, becomes more and more negative, the magnitude of this is going to increase. And you can see that this increment will happen till the phase error is equal to 2 pi, because now only the rising edges of the two signals are being processed and nothing else matters. So like the previous case, so here also the phase error is going to continuously increase up till 2 pi, but DC is going to be negative. So now if we combine the two cases, then the characteristic is going to look like this. So this will increase to 2 pi. Similarly, it will increase to 2 pi. And after this, there will be repetition of this curve. Here we see that for this PFD, we have a wider phase detection range. So theta E can vary from minus 2 pi to 2 pi. Now we can quickly see that how this will also allow the reduction of phase error. So we find that when we have this uh, case 2 where the phase error was negative, a negative DC voltage is produced which will be fed to the VCO. So it is this quantity which will be fed to the VCO. So this is going to be the input to the VCO, this quantity. So now we see that if we have this scenario where omega r is lagging, so what will be the response of the VCO? We know that VCO is given characterized by this plot. So what we see in this case, negative voltage will be fed to VCO. So that will then reduce the output frequency. So this is the output frequency of the VCO. When omega naught reduces, this will imply that omega d reduces. That will imply that omega d rotates with a slower velocity. And in that case, this omega r will be able to reduce this phase error between the two signals. And similarly, for this case also, we see that positive voltage will be fed to the VCO. So when the positive voltage is fed for positive phase error, the output frequency increases. So output frequency increases, this implies that omega d will increase and then it will be able to reduce this phase error. So that is how this circuit will be allow the reduction of the phase error. As the name of this detector suggests that it has the ability to sense the frequency gap between the two signals also. So we might have a scenario where the frequency gap between two signals is very large. Say for example, we can have a scenario when omega r is large compared with omega d. We can take a certain example that omega r is equal to 4 times of omega d. So that means the time period of d is going to be 4 times of the time period of r. So reference signal will change very fast, and for every 4 cycle we will have only 1 cycle of the difference. So we can now see that what will happen. So we have V R like this, a very fast changing signal. But VD is slowly changing signal like this. So here we have a we should have 4 clock cycles. So this is going to be our VD. Now it is these rising edges which are important, which will be used to process the state machine. We see that we have rising edge of VR occurring before the rising edge of VD. So what will be QR? It becomes high. It goes into state 1. and rising edge of Vd, so it will bring it back. But then after a short duration, because VR is very fast changing, so we will have another rising edge of VR, and then it will remain high till here where the second edge occurs. So it will remain in state 1, it will be kept in state 1, and at this age also it will be maintained in state 1. Only here where this rising edge of VD occurs, it will be brought back to 0, state 0. But then after again a short duration, it will again move back to state. So this is state 0, this is state 1. So at every rising edge, it will be retained in state 1 and then brought back. So here we are assuming that there is a slight mismatch like this. So this one occurs after the VR edge. So here we see that we have QR, which has a wide pulse. And now let us see that what will be QD. So for QD, we see that when we have state 1 for QR, that time it will be 0. And when it goes into state 0, it will of course remain 0. And since it has gone into state 0 or state 1, so QD is of course going to be 0 all the time, because in state 0 and state 1, QD value is equal to 0. So here we have QR minus QD wide pulse, or a rectangular waveform with a large duty cycle. So this implies large DC. So QR minus QD average is going to be large DC. So what will happen with the large DC? So what we have here is that this kind of scenario. So here we have omega r, and it is rotating at a very fast speed. And then here we have omega d, which is slow. Right. So what we see here is large DC is produced by PFD for this scenario. And initially we have assumed very small phase error. So here very small phase error. So like this. So now we see that what is the characteristic of VCO? Sorry, for VCO, this is not going to be theta E, but rather this is going to be input, which is going to be QR minus QD average, the DC of this different signal. And this output is going to be frequency, output frequency. So here system will be somewhere here, anywhere, but then we see that a large positive input voltage is now being fed to the VCO. So a large positive means somewhere here. So that means the output frequency of VCO is going to increase by large amount. So we see that this large DC, this implies large omega naught. So this will imply large omega D, because this is obtained by dividing this omega naught by factor n. So when this omega D increases by large amount, it will be able to minimize this phase error, because keep in mind that omega r is rotating at a very high speed. So this phase error, which is very small in the beginning, is going to increase with the time. So it will increase the omega D with this large DC. So it will try to track or the minimize the gap between omega r and omega d. That means it will try to first minimize the frequency gap between the two signal. So we see that this PFD has capability to minimize the frequency difference if at all there is a wide frequency mismatch between the two signals. Similarly, we can take a case where we have a reverse scenario. That means omega r is less than omega d, and we can again take the example that omega r or 4 times of omega r is equal to omega d. So this says that the 4 times of time period of d is equal to time period of r. So we have this Vd and Vr. So Vr frequency is less, Vd frequency is high. So we will have this kind of situation for Vd. And Vr is 4 times. So we have this type of waveform for Vr. So now let us see that what will be QR and QD for these case, and what will be their difference, and how this will PFD will allow along with the VCO to uh, minimize this frequency error. So here we see that the rising edges of VD are obviously going to occur with more frequency, and they will occur earlier compared with VR. So we can assume that this rising edge is somewhere here, occurs before the VD. So we see that both the system, they start from 0, 0, but the rising edge of VD occurs first. QD is going to become 1, and but then after a short duration, let us say that the rising edge of VR occurs, so it will return back to 0. So this goes to state 2 and remain there for short duration, and then again come back, and again comes back. So it goes to state 2 for short duration, then again comes back to state 0. But it will remain in state 0 till this first rising edge of VD. So where it will again be pushed to state 2, where QD will be 1 and QR is going to be 0. So we know that in state 2 and 0, QR is 0. So uh, it will remain in state 2 till the second clock age, and then no clock age of VR occurs. So it will go up to third clock age. So it remains in state 2 till the third, and then let us say that rising age of this occurs before the rising age of that. So this fourth one occurs first, so it remains here, and then this first stage of the VR occurs, so it will then bring it back to 0. But then after a short duration of this much, again system will be pushed to state 2. So here we see that it will again remain in state 2 for long duration, and then brought back to 0, and then again pushed back. So here we see that we have a white pulse for QD and 0 for QR. So now if we see QR minus QD, we are going to get a negative pulse. So this is level 0, this is 1. So we are going to get 0, and then -1, then 0, then -1, like this. So this is 0, this is -1. So this we are QR minus QD average is going to be large negative value. So we see that this time the VCO will be fed with, this is equal to QR minus QD average. So this will now, since VI is negative, so this will be fed with smaller frequency. So when this is large negative, this implies that omega naught goes down. This implies that omega D goes down. And so this is the problem here. We see that the omega D frequency is very high. So this scenario will try to pull back the frequency of the difference, the VCO output or the difference, and hence the uh, omega T, which was moving at a very high speed compared with omega R. So it will slow down. It will slow down. So this frequency gap and ultimately the phase error will also get reduced. So this is how this will be able to help the minimize the frequency gap and finally the phase gap also. And once these two frequency they become equal, we have already seen that if there is any phase error, that will also be reduced. So we see that the this PFD will try to reduce both frequency gap and phase gap or error. So both of these mismatch or gap or error between the two signals will be uh, minimized. But ultimately the frequency will be made equal also. So we have seen three digital phase detectors, XOR, and then SR latch and PFD. So we can see that how they compared with each other. So here we saw that the XOR gate had this kind of response. So it was capable of detecting phase error only up to pi. So this is XOR, and then SR latch was able to detect the phase error up to 2 pi. Like this. But this PFD, which is more capable, and it was able to detect phase error over a range of 4 pi. So it can detect phase error up to 4 pi range. So these are characteristics of three-phase detectors. So now for this PFD, we will first try to see the circuit, one of the possible implementations. So it can be implemented with the help of 2D flip-flops. So where the inputs will be actually fed to their clock inputs, and the actual input, it will be always maintained to value 1. And we take these outputs. And we have AND gate, which is used to reset these two flip-flops. So this is QR and this is QD. This is one of the implementations of PFD. Now we will see that what is the circuit which is used to find the difference of these two, and then also find out the DC of the different signal. There are two additional circuitry which are cascaded in front of this PFD to find out the difference and ultimately the quantity which will be proportional to DC. We use a circuit called charge pump. And we use capacitive low pass filter. So these two additional elements are cascaded at the output of PFD to find out the voltage which will be fed to VCO. So we have here our PFD. This VD will be coming from divider, and then we have QR, QD. Charge pump is basically a connection of this current source two current sources of ideally same value, and connected to a low pass filter. In the simplest form, this is going to be only a capacitor C. So here we have now three elements. Charge pump. So charge pump is this much circuitry. This is charge pump, and then we have filter here, and this will then produce a voltage VI, which will be ultimately fed to VCO. So what we found is that whenever phase error is positive and large here, for example, then we see that large DC will be produced. So let us see that how large DC will be produced if we have a positive phase error. So we saw that whenever a positive phase error occurs for positive theta E, what we found is that QR is high for duration proportional to phase error, and QD is low. So what will happen is for this case, this switch will be closed while this is on and this is going to be off. So if this happens, what will happen is there will be current from this what is called pull-up source, and it will pump charge into this capacitor, and this voltage will go up. And it will keep on increasing as long as this QR is high. So if there is a more phase error, if there is more phase error, there will be larger duration for which QR is going to be high, and there will be larger duration for which this switch is going to be on. That means charge will keep on accumulating in the capacitor, and this voltage is going to increase. So that will finally increase the output frequency and ultimately the difference frequency. So this is what happens when we have a positive phase error. Now, what happens for the negative? For negative phase error, so for negative phase error, we will have reverse scenario. That means now this lower switch is going to close down, and what will happen now is whatever voltage was accumulated in the capacitor, or the charge was accumulated, now that charge will be pulled out from the capacitor. So charge will be pulled down to the ground, and this Vi is going to reduce. When Vi reduces, the omega naught is also going to reduce. And we saw that this will happen whenever frequency of this Vd is more. So it should be brought down, and this is how it will happen. Now we can calculate or find out the expression for this Vi, how this Vi will vary with time. What we see here is that whenever QR or QD pulse occurs, say for example QD pulse occurs again and again, so there will be a short duration for which charge will be pumped into the capacitor. Let us say that the phase error is positive and small. So in this case, what will happen is this QR is going to be a pulse like this. So QR is going to be like this. So what will happen is the first switch, this S1, this is S2, S1 will be on for this duration, and it will be off for larger duration, then on, then off for larger duration. And QD is going to be like this, 0. So this is the status of switch 1, and switch 2, this is going to be off all the time. Here this remains off only for this much duration and on for this duration. So switch 1 is going to be closed, and then for short duration charge will be pumped into the capacitor. So this Vi will rise. So now if we plot the Vi, what will happen is, suppose that it was certain level before switch started, or we can assume a 0 level also. So let us plot the Vi. So we assume that Vi was certain voltage when the system started. So switch is on for very short duration. So voltage will rise like this, and then switch closes off. Both the switch are off for this duration. So the voltage in the capacitor will be maintained because there is no path for discharge. And then again, second time, it switches on. So voltage will rise by a small amount, let us say almost by straight line, and then for this much duration it will be maintained constant. So this is how the Vi voltage will increase. Now keep in mind this is equal to the phase error, and this much is the time period. So corresponding to this phase error, we will have a time delta t, which will be equal to theta e divided by 2 pi into t. So this phase error corresponds to this much of duration. Now our objective is to find out what is this rise in the voltage, this voltage. Here we know that current into capacitor is given by this equation. So this can be approximated to, here we have the current equal to Ip into dt, which is delta t approximately C delta V. So we see that rise in the voltage delta V will be equal to IP by C into delta T. And this delta T we have already found out is equal to the phase error divided by 2 pi into the time period of the waveform. This much of rise in the voltage will occur for theta e phase error. And this rise in the voltage occurs for a duration equal to t. Although it occurs actually for duration delta t, but overall voltage rise in one cycle is same thing delta v. So in one cycle, in one time period t, the net increment in voltage is v. So we can find out what is the average increment in this voltage. So we can find, so that average is going to be rise in the voltage and total duration, which is equal to IP theta e by 2 pi c. So we see that in every cycle, the voltage rises by same amount and the cycle duration is also same. So this average value is going to be same. So if we find out this average value will be like this. So this average value is actually going to be the slope of this line that we have drawn here. So we can now approximate this VI by this black color plot, which is say 0 up to here, and then it rises with a constant slope. And that slope is going to be equal to this. We can now write equation for this VI. This is going to be VI is equal to this slope into T. This VI is IP theta E by 2 pi C into T. But here T is equal to 0 moment is this one, and it is 0 value before that. So for that purpose, we can multiply this by unit step function U also. So this is the expression for the input voltage to the VCO. And this is how the frequency of the output of the VCO or the VD is going to be decided. But this is for the simplest implementation where we have taken only one capacitor for the low pass filtering. But then there are certain issues with this. So those are sorted out by taking a different type of a low pass filter, which extracts the DC of QR minus QD. So that gives rise to different expression for this VI. And that of course is now going to decide how the tracking occurs, how fast, how slow, and in one shot or in with certain ripple.